Hello and welcome. My name is Nordling and I'm an assistant professor in automatic control at the Department of Mechanical Engineering at the National Shandong University in Taiwan. I'm also the general chair of this workshop. Behind me I have the Tai Chi shadow boxing monument created by Su Ming in 1983. The monument represents the individual's posture and strength, demonstrating the resilience and harmony of the two opposing forces. Now it's my honor to introduce our honorary chair, Chair Professor Wu, who will have a welcome message for us all.
It is a pleasure to welcome all of you on behalf of the National Shandong University in Taiwan. I'm proud that our team, the NCKU Parkinson's Disease Quantifiers, are one of the finalists in the OpenCV AI competition. They are also arranging this workshop. Now let us all learn computer vision and AI using the Ph.D camera together.
I'm glad that you have joined our over 950 registered participants for this lecture on computer vision and machine learning for aerial autonomy by my good friend, Dr. Alberto Speranzon. Now, you are welcome to subscribe to our YouTube and Twitch channels and to press the alarm button if you wish to get notified about future videos that we post. Now, Alberto received his Ph.D. degree from KTH, the Royal Institute of Technology in Stockholm, Sweden in 2006. Meaning that I spent the first year of my PhD studying together with Alberto, and we became good friends at that time. Now, Alberto today is a technical fellow at Honeywell Aerospace, where he is working on applying machine learning and artificial intelligence to very challenging problems in the aerospace industry, and the transformation towards the use of autonomous drones for packet and personal delivery in cities. Now, he will today be giving a very beautiful lecture on this topic, so please enjoy.
Hello, everybody. I'm Alberto Speranzon from Honeywell Aerospace, and I'd like to thank Torbjörn for the invitation to speak about computer vision and machine learning for aerial autonomy. So in particular, I will be speaking about two application domains. One is related to image processing for UAV-based inspection. So the idea here is to have an autonomous drone taking different type of images of different type of infrastructure and doing some analytics on it. And the other application I will speak about is on computer vision for urban air mobility, which is this new area in aerospace, which sees the deployment of new type of vehicles, mostly electric, transporting both goods and people within large-scale cities. So if we start with the first application, really this encompasses the use of a UAV for taking information about different type of infrastructure from power line to refineries. And I guess, fairly commonly the process that is used to inspect this infrastructure starts with a plan, which is, using prior information to develop what route the vehicle needs to take, which is then uploaded into the vehicle itself, which is moving around the infrastructure, taking various type of information using onboard sensors. We mostly focus here on cameras. And this data then is uploaded onto a cloud, which is then processed, and the processed information is provided to the inspector. So really, this project had the focus on the analytics on the image. And why that is important is because this type of vehicle can very quickly collect a huge amount of data, and it can become overwhelming for the inspector to look at every picture to try to understand if there are interventions to be made. So the purpose here is to semi-automate the analysis of this imagery using machine learning. So the first thing that we looked at was actually detection and segmentation of cracks. The reason for that is cracks are an issue that appear in many different types of infrastructures. So having a machine learning capable of doing that can be applied across different spaces, and is very important because cracks need to be taken care of. They signal potential failures of the infrastructure. So for the detection, we use a UNet with dilated convolution. And the reason why we settled for that was that in 2018, 17, 18 was a Chicago competition on segmentation. This was one of the key networks that scored very highly. And so we used this for our segmentation problem. For the training, we had only 1,000 images labeled. And of course, we did an augmentation using rotation and flips. We used at the time just 8 NVIDIA board to do the training and the exploration of hyperparameters. But still, we were having issues to get good results, especially on faint cracks, so very small cracks, which are very important to be detected. And so to mitigate that problem, we actually extended a mix-up augmentation, which in the original paper takes inputs and blend them, taking linear combination of different inputs. Turned out that this strategy was not working sufficiently well, and we actually settled for just a union of labels as a mix-up. So here you can see 2 different imagery that are mixed up. And the reason why this actually worked very well is that by mixing different cracks, which then each image is rotated and flipped, but then mixed with others, really provided a way to sort of simulate, in some sense, new cracks in an image. We were having very hard time to try to create synthetic imagery that looked real. And so this actually augmentation worked really well to enhance the number of training data that we had. And so here are some results that we had for this analytics. So here is actually a deck of a bridge made in concrete. This line that you see here is just the extension joint between different parts. And in this colored part of the image, you can see the detection of cracks. And it's working pretty well. As you can see, especially here, there is this section of this crack that is quite faint, but we're able to detect it quite well. There are some false positive here, but as you can see, we are weighting them less. So the neural network provides a likelihood of this being or not being a crack, and so this actually is marked as not being likely a crack. As you can see, there are some mistakes like here, where we are confusing the expansion joint for a crack. But as you can imagine, these are pretty high resolution imagery, and being able to provide to the inspector or attract the attention of the inspector to the specific areas where cracks are makes their job a lot simpler, as they don't need to go through every part of the image looking for cracks. So really the idea here is to use machine learning to attract the attention to of the inspector to the key areas that may need to be considered by an expert and decision made if intervention needs to be taken. Also notice that the concrete is highly textured, but the neural network is able to not get confused by this highly textured background or pattern in the concrete. Another project that we did also connected to infrastructure inspection was the localization and georeferencing, georegistration of power poles in a power line. So as the power line get adapted to construction that are happening around it, or poles are replaced, but maybe placed slightly off from the original one, there is a problem for the infrastructure owner to know exactly the location of where these power poles are. And so the idea here was to use the vehicle that is already flying over the power line to also geolocalize where these power poles are, and ensuring that the GIS system of this infrastructure is up to date. So for this, actually, we used a combination of two processes, one using point cloud and another one using image segmentation. And I'll explain a little bit more what this means. So as the drone moves along the power line to do the inspection, what we end up with is a large amount of images which are used in a structure from motion software to create a 3D representation of the environment. Out of this, we can then do a processing of the point cloud where we extract every 3D object that is extending upwards from the ground plane. Now, one could potentially use a deep network to directly take this point cloud to identify what is a power pole compared to a tree, for example. The issue with that is that we didn't have very good model, 3D model of power poles. Secondly, the reconstruction of these power poles is actually not very accurate. There are missing parts, holes sometimes happening. And the reason for that is that we are flying along the power line, first in one direction and then coming back. And we don't have really a 360-degree view of the environment around the power pole and the power pole itself. So it becomes really difficult to reconstruct these precisely. So what instead we did was that every point in this point cloud is coming from at least a pair or more images that have been correlated. And so for every point in every vertically extended structure, we can actually run machine learning on that particular set of images to understand if what is contributing to this 3D structure is actually something that is it's a pole. And so here you can see the segmentation that is able to detect that there is a power line pole. And so out of this, we can filter what are structures that are likely to be poles compared to trees. Now you probably wonder, why did we do a segmentation and not just an object classification? The reason is that this part of the algorithm is also used to find cracks. So we reuse the same segmentation both to identify if these 3D structures are poles, but also to run the crack detector over the mask representing or identifying a pole. And so out of this, using then the ground plane, we can detect the intersection between this 3D structure that has been classified as a pole, and the base plane to find the base, and from there, since this point cloud is geolocalized with the GPS of the drone, find the position of the base of the pole. So going one more step in detail about the segmentation, we also at that time used the UNAT with a decoder that was similar to the RSNAT. And as an encoder, we use for a small version of the network using a RSNAT 34, but we actually got better results using a WideNet ResNet, but that required a bigger machine for the training. Now, the biggest challenge that we had was the training of the network because we didn't have much imagery of real power line poles and electrical poles. And so we had only 100 hand-labeled images. And so what we relied on was a fairly large library of power pole in simulation. So now what this also allowed us was to look at different type of orientation, different type of power line poles. And despite the fact that the simulator was fairly crude in the representation of the environment around the power line pole, we were able to get pretty good results using these 100 hand-labeled images as validation set mostly. And as you can see, we are able to extract we are able to do the segmentation of the power line pole here pretty well. So this is just a high-level overview of some of the things that we've done in trying to cut down the time that it takes for inspectors to process images collected from a drone. Now, moving to the second application, which really came along out of the experience that we gained from processing images from drones, but also given the push that there is on the use of this new vehicle for transporting people and goods. So we migrate some of that experience in this environment. So why is this important? It's really a revolution at this moment in aerospace that goes under the name broadly of advanced air mobility, and is really pushed by the fact that there is more and more online retailing that requires faster shipment of all kinds of packages from warehouse to warehouse, from warehouse to homes. And the other one is obviously traffic. So urbanization is really leading to larger and larger traffic jam, and it's becoming extremely time consuming to go from point A to point B within a large city. And so really, when I speak about urban air mobility or advanced air mobility, we're really speaking about the motion of cargo and packages, as well as people within large scale city or within small regional areas. Now, this may sound science fiction for those that maybe are not in the aerospace community. It's actually pretty real. And here are some of the companies that are actually developing the vehicles. There is quite a bit of activity on the cargo being the first application. This obviously not having people on board makes the safety requirements a bit more manageable. Whereas for urban air mobility, which is transporting people, the concerns on safety are very high. But you can see that there is intention to get initial entry into the service in the next 2 to 5 years. Of course, in the very beginning, this will be mostly human piloted, but the key for making this technology possible is to make the piloting effort much, much simpler. So, if you look at a cockpit of an aircraft today, it's extremely complex system that requires highly, highly trained pilots. On the other side, you have Tesla that is, highly automated, almost autonomous. And so what you need to be able to get these vehicles to take off in terms of, a product, you need to make the barrier of entry for people to be able to pilot this much lower. And so really the industry is looking at new ways to make the piloting much, much simpler. So this is just a concept of how the cockpit of the future for this vehicle should look like. Obviously, there is going to be just a single pilot. As you can see, the cockpit is much, much simpler. And of course, to be able to achieve this, what we need is a lot more automation and ultimately autonomy into the system. So if we look at the pipeline of an autonomous system, it's really, at a high level, composed of 4 main blocks. Usually this goes under the acronym of OODA loop. And it's really, fairly natural. We observe the environment, we understand it, we make a decision, and we act. So going a little bit in detail on what we're doing in this context. So the observe, it's really the part that takes the raw measurement from sensors and it transforms them into contextual information that can be used to understand the information or how the environment is around us and who is around us and so on. Where are we in the environment? Usually, a single sensor is not sufficient, especially if you want to be able to fly at night, maybe when there is weather. And so at Honeywell, we're looking at a very large range of sensors, including cameras, radars, and similar sensors. But the more interesting part for this talk is the orient part, which is really taking this raw information and sort of understanding in a way that can be used to make sense to the world around the vehicle. And also this is needed to be able to make decisions. So the orient part is trying to take raw information and make context, create context around it, which is useful for decision making. So I'll give you a couple examples of things that we are doing. So here is, for example, the work that we are doing on landing site detection and automatic landing. So here we are using QR code-like markers to aid the vehicle towards the landing area. It's used both to understand the correct landing pad, but also to be able to position the vehicle with respect to the landing pad. As you can imagine, a GPS would not provide sufficient accuracy to land precisely on a small landing pad. And so here you can see the detection of the QR code and the positioning of the vehicle with respect to this QR code enable us to place a location to the center of the landing pad. So generally, we test these things on small drones to validate the behavior of the algorithms. And here is something that we've run close in our facility, where you have a drone that is approaching a landing area, and the algorithm detects the landing area and then localize itself with respect to the area, the landing pad, and then computes a descent trajectory towards the endpoint. So for this algorithm, obviously, the final application is not going to be just drones, but also these bigger vehicles that are going to be carrying people. And so once we have validated algorithms on this smaller vehicle, we do test them on actual helicopters. And here is some work that we've done in Arizona, where we have used an helicopter to see how the algorithm behaves in a more complex environment, much larger scale, and so on. Now, the algorithm that we are using here actually is, we have actually two types of algorithm. One, which is using more standard computer vision methods, leveraging the fact that we have this very structured type of landmarks that we're looking. But we also are looking at machine learning methods, especially those are useful for identifying areas where you want to run your classical computer vision algorithm. So you can imagine that trying to find the QR code in this complex environment can be much faster and more efficient and more accurate to use a neural network to find bounding boxes, and then using a just a standard computer vision algorithm to find the exact location of this QR code. Another area which is, again, taking low-level information but trying to extract high-level contextual information is this work that fully use a deep network to try to find an emergency landing. So as you can imagine, this vehicle can have issues at some point and may be required to do an emergency landing. And so here we have used a simulation to validate some of the initial results. So I will show a video. On the top right, you will see a heat map. This actually is produced by a deep neural network, which combines a lot of different kinds of information, from some reconstruction of the depth map, as well as some information about the objects or the things that are around the vehicle, and a red area, a dark red area, is a potential good landing spot, whereas yellow, bright yellow, is not a good landing area. And then on top of this, we can fit a circles, actually two circles, which identify sort of the minimal and a buffer area around possible location where the vehicle can land. So the video that I'll show in a second will show the vehicle that is navigating in this environment, and at some point it will have a simulated failure. At that point, when that happens, it will try to use a landing area that is just beneath it to attempt a emergency landing, but this may not be available. If that is the case, which is what's going to happen in the simulation, it will take a landing zone that has been stored in the database and go back to the nearest one to attempt an emergency landing there. So here is the situation. You can see that the landing area changes based on the availability of really space. Sometimes there is, as you can see here, there is area that is flat enough and out without big trees and the like, but then not big enough. And so here there is a failure. As you could see, there was no area to land on. It was very crowded with trees, and so it goes back to a previously recorded area, which is safe to land, and so it executes the landing. So this is some work that we are continuing to extend this, not just to this sort of outdoor environment with trees and so on, but also to work within more urban and suburban environments. Now, Just a couple of words on actually some of the work, part of this OODA loop, which I work probably the most, which is on the decide part. So being able to detect that there is a landing area, for example, for doing an emergency landing is great. But ultimately, you need to decide if that is the best place to land. And secondly, if you should be landing at all, or should you attempt something else. So making the decision is the critical part that today we rely on, mostly humans to make. And so to achieve more autonomy, we need to be able to make the decision and act blocks very safe. And that's probably the biggest challenge of autonomy is how do we make this decision and action safe? And typically, the decision and action can range from, just mission level. So we decide that we need to start from A and we need to go to B, and what is the route that we want to take, and what modification to the route we want to take as issues appear. But they can also span very fast time scale and spatial scale, like the emergency landing, where things needs to be decided, at the level of seconds or even less than a second on a space that probably is only a few meters large. So really, that is really one of the biggest challenges in autonomy, is to make this complex decision when contingency arise. And the other problem is that we need to be able to certify that these decisions are safe. So that is really probably one of the most complicated part in aerial autonomy, is the safety requirements. You need to be able to demonstrate that the system is safe, and that is really, really challenging, given the infinite many possibilities that the vehicle may encounter. And today we rely on humans to be able to do that. So if we look at these two, we spoke about these two sort of different application domain, the inspection and the urban air mobility. So is there any connection between this? Well, there is, and really it's as a common objective, there is this intent to make the system a lot more automatic and autonomous, so that it's able to make a decision that either simplify and reduce the human effort. It certainly is the first, and then ultimately at some point really reduce the presence of human in the loop. But the big challenges that we had in both settings is really the lack of large data set to train the neural networks. As you can imagine, what happens if you need to do a landing when there is rain, and when there is we are dusk or sunset and so on. So we rely a lot on simulation environments to do that. But as you can imagine, these are very difficult to represent outdoor environments. And so that has been something that we've been working on and try to understand how we can do better to bootstrap model using simulation, but that is more representative. The other thing that we use simulation is to find sort of corner cases. As I said, safety is critical in the system, and so becomes extremely challenging to do this on a real system to find corner cases, and so simulation becomes very useful to do that. The other thing is that when you look at aerospace, especially things, vehicle that carry people, the level of accuracy and safety is extremely, extremely high. And today, neural network, for example, while they are certainly very, very accurate compared to previously known algorithms, they do not achieve the level of accuracy that and safety, in some sense, that is required for aerospace. And so there is a lot more work to be done to understand what are the safety implications of this new type of algorithms when deployed on aerial vehicle especially that carry people. So with that, I would like to thank you, everybody, and hope I will have the chance to answer some of the questions. Thank you.
Good morning, Dr. Speranzon. Good morning,
Hello, everybody.
Welcome to join our Q&A session. Thank you very much for the great talk, and thank you for willing to join us online. We have gathered some questions from the YouTube chat and Twitch chat. Let me speak them out one by one for you.
Sure.
So the first question is, your conclusion that neural networks are not accurate enough is very interesting. What do you imagine would be more accurate? Which research track is that you follow?
Yeah, so I think that it's not so much about what could be more accurate per se. It's a little bit more complicated than that. Can you hear me?
Yes, but it seems that
something happened, right?
Yeah, the camera is stuck there.
Yeah, I'll continue speaking if you can hear me at least. Yeah, so the critical piece is obviously to try to make things more accurate, but for safety reasons, what really is critical is being able to understand when an estimate from a network may not be correct. So that is one of the difficult part, is that no matter what input you provide to a neural network, it will always provide an output. The problem is that that output may be wrong because, for example, input is out of distribution. And so this is really detrimental for the system if you consider that input to be always correct and accurate. So I think that that is probably the more, when I said it is not, you need something more accurate for sure, but there's also this implication of knowing when a neural network may be wrong. So that is really the most important thing.
Thank you very much. The other question is from Twitch. The first one is, interesting project of crack detection. Does that also work on non-smooth ground?
Can you repeat the question?
So for the crack detection, does that also work on non-smooth ground?
So I don't know what exactly not smooth means, but we tried it on, for example, power pole that are made in wood, which is not super, flat, concrete, asphalt and the like. If you're considering something that is very rough,
it seems we have some technical problem. Please give us a few minutes. We'll solve the problem. It will be online.
Yeah, I can hear you.
Yeah, welcome back.
Maybe the camera is eating up all the bandwidth, so I'll keep it off if it's not a problem.
No problem. Okay, shall we go to our next question?
Sure.
The next question is the QR code safe? Can someone make a fake QR code and trick the airplane going somewhere else?
Yeah, so usually when you consider safety, it's something that needs to depend on the context. So there is not absolute safety. So you need to consider all the risks and mitigation factors. So it's clearly, if a urban air mobility vehicle needs to land in a place, it's not only using the QR code, right? So the position, the information about where the landing location is going to be part of the decision making for the vehicle. So it is not possible in general, right, to just paint a new QR code somewhere and then have the vehicle to land. That said, there are complications because we are still using visual information. So, if there are debris or dirt on a QR code, it could affect the safety in some sense, because we don't recognize the correct ones, or we not able to recognize it at all. And so these are things that needs to be considered in the risk plan and mitigation.
Thank you. The next question is so far the last one. So his question is from Sebastian. How can we ensure that small object could be detected with high accuracy?
Small objects, in what context? I'm not sure if I follow the question fully.
Okay, thank you. Oh, we have another. Yeah, we have another one in YouTube. How to convince public that the automated vehicle is safe?
Yeah, that's a very, very good question, right? So the process that we follow in aerospace has been sort of tested over many, many years, right? The same way that you can sort of claim that today aircraft are safe is because they go through a lot of requirements or certification processes. The pilots that are on board are trained, and they keep training. So for autonomous system, the first thing which is completely missing today is what are the regulations to claim that the aircraft is going to be safe if it is driven by autonomous system. Today we don't even know what those rules are. But as you can imagine, as we learn more and we develop more of these technologies, there will be regulation. So this means tests. You need to demonstrate that the vehicle is going to be safe through multiple different agreed tests. There will need to be software that needs to be tested, hardware that needs to be tested in various kind of conditions. So it's a good question. I don't know if we have an answer yet, but I think that that's really an important key question of how do we guarantee that an autonomous vehicle will be safe.
Thank you very much. Just about the question of small object with high accuracy. He also mentioned more information like aerial imagery, just like crack, or boats in the ocean, or missed persons on the woods. Every kind of object could be visualized over UAV altitude limits. That's the information he had.
Yeah, obviously, you always need to have enough pixels on target to be able to identify that object. So I'm just thinking about things that we may have done, where we are trying to search for small objects. I can't really think about anything specific, but I think the limit is going to be always, if you have enough pixels for target. I mean, for example, in the QR code setting, as you can see in the picture, there are different sizes of QR code because of as you are approaching from a certain altitude towards the actual landing, the QR code, the bigger QR code, get out of the field of view. And so you use the smaller one. The small one, for example, we are not able to detect it precisely when you're very high up. And so that's the reason why you need to use bigger one to make sure that you detect. So, it's going to be a function of how many pixels you have on target, and also the accuracy that you're looking for. So, we're trying to be very, very accurate to detect these QR codes. So small ones, although we can detect them, they're the probability of detecting them correct is not sufficiently high to rely on them, and so that's the reason why we take this bigger one. So yeah.
Thank you. Another question on YouTube is from Austin. Thank you for your presentation. We see that the drones interact well to the environment. How well will they interact with other drones?
That's a very important question. Is not just with other drones, but is also with other aircrafts. As you can imagine, if you are navigating in a city, there could be emergency helicopter, for example, that are landing on a close by hospital. So you need to make sure that there is no collision. So usually for things like that, we tend to use radars rather than cameras, although you could augment radars with camera, but that is a typical problem that happens in aerospace all the time, where you may have a collision, and so radars are used to ensure that you're aware of other vehicles around you. And also usually you can distinguish cooperative traffic and uncooperative traffic. So cooperative traffic is other traffic that is using transponders to signal their presence around other vehicles. So this is typically what happens in a regulated airspace. Of course, there may be someone that is just using a drone or some other vehicle which does not have the transponder. That's really where the radar becomes very, very important to be able to detect those and, not just detect them, but also predict where they're going to move.
Thank you very much. We still have few minutes, so maybe we can wait for few minutes. If someone
Sure.
wants to ask more question, please feel free to just put in the chat. And also for the more information about our workshop, we'll have our another workshop tomorrow on Thursday, 10 a.m. Welcome everyone to join that. Okay, I think there's no one asking question now. So I think this is today's workshop. Thank you very much for the answers. And
Sure.
thank you
so
for
much
willing to join us. Thank you,
Yeah,
everyone.
thank you for the opportunity.
Dr. Speranzon.
Have a good day. Take
Have
care.
a good day. Bye.
Thank you. Bye-bye.